the title of this session is Earth Resources for a Changing World. So in 2019, as Chris mentioned, Ireland officially declared the climate, but also the biodiversity, that we are in a climate and a biodiversity emergency. And as a result of that, we had a succession of climate action plans. The European Union also has set several goals, including the very important one to become climate neutral by 2050. And in Ireland, goals were set for 2030 as part of these consecutive climate action plans, including significant reductions in the greenhouse gas emissions, an increased proportion of renewable energy in our energy mix, and of course, increased energy efficiency in our buildings and so on. So an energy transition is therefore required. And so you'll hear about iCRAG's work on the energy transition in the next session after the break. I'm going to focus on the other part, the resources that we need, and a huge challenge that we need for this energy transition, because many of the geoscientists in this room will know that we do need a lot of extra materials that we haven't used before, a lot of metals we haven't used before in raw materials to enable the photovoltaic cells, the wind turbines, etc. of the world. So this ties in very much with iCRAG's research, and the speakers that will follow on from me will highlight how iCRAG is addressing some of these key challenges. Key challenges in order to address this, to ensure a reliable and a sustainable supply of critical and raw materials. So this is to discover more primary raw materials, to ensure more and increased recycling, and also to make sure that any discovery that we do is sustainable and safe. Right. In 2023, the European Commission and the European Parliament approved the European Critical Raw Materials Act. It will be known to many of you in the audience. And essentially this sets benchmarks on our critical raw materials within this bigger challenge of the energy transition. This legislation has trickled down to Ireland and the member states, and it's currently being, and implementation plans are currently being discussed and being worked out. So the Act sets 2030 benchmarks for strategic materials, including increased production, recycling, and processing of raw materials within the EU. And importantly, and often people forget this fourth point there in terms of that's on that slide, is to alleviate supply risks to Ireland and the EU. It's critical that we ensure a sustainable and a risk-free or a lower risk supply of raw materials. So there's a target of no more than 65% of any raw material should be by 2030 from any single third country to alleviate that risk. So this means that we need a global view, and you'll see in some of the research that will be presented by the next speakers that our research is global and has been from the start, especially in the raw materials. iCRAG, since its inception, has also been at the forefront, as mentioned by the previous speakers, addressing this within the policy framework. So iCRAG researchers have been linking into raw materials policy at the EU level, including making sure that the research agenda of Horizon Europe and Horizon 2020 before that has the right calls and targets to address these challenges even before the Raw Materials Act was made. And we've been building partnerships over the last decade with strategic regions in the world, especially, for example, with the EU-Africa partnerships. Okay, a final one here is building materials and materials for infrastructure development. So raw materials also include everyday products, aggregates, sand, gravel, and various constituents for building blocks. Right? The transport infrastructure, construction, and utility sectors are crucial for our economy. They're growing, but they also face key challenges in terms of sustainability, the unpredictability of our climate. And so since its inception, iCRAG researchers have been working with these sectors, on research, for example, in road aggregate research for road safety, and novel cement printing and binders, as well as investigating the issues around the defective building blocks, a problem well known in Ireland, costing homeowners and the Irish state greatly. So that research has led to a number of contributions to national and European standards, which I think have been a key output. Crucially, and to close up my part, Earth resources for a changing world are taking place in a changing world. And therefore, these issues affect everyone, everywhere, and including the publics, as was previously mentioned. So you will now hear from Associate Professor Geertje Schuitema on the EU Vector project, which is a flagship project that's helping to understand how technological advancement in understanding raw materials has to and can remain human-centered. So, Geertje.
Thank you very much. So in retrospect, I wish I had labeled this 6 minutes contribution, "Does humankind want to be saved by geosciences?" Because I'm a psychologist by training, and I won't go that far, and I won't spend my 6 minutes on this, but I'll touch on it a little bit. So I'll be talking about a European project that has run for the last 2.5 years, and it's called Vector. And just to summarize what Koen just told us, the EU is decarbonizing, which means a lot more demand for critical raw materials, wind farms, solar panels. Energy demand is rising, as Chris just said this morning. And therefore, and at the moment, the vast majority of critical raw materials are exported, so coming outside of the EU. The EU wants to change that. They want to mine more raw materials within their borders. So this project that I'll be talking about is looking at how can we access critical raw materials in Europe. There's a whole technical side. How can we do this technologically? Look at the geoscience. I'll focus more on the social science elements to this. So what are the societal challenges to actually be able to do that? And how can we actually design policies, change business models to facilitate this? So the background to this story, and I know 90% might guess, people in this audience will think, another project about SLO, social license to operate. We don't really research social license to operate. We actually look way deeper into what is relevant. So the background to this project lies a little bit in this data. This was a survey done in 27 countries, looking at different industries, and the general public was assessing what their performances were in social responsibility. Now, for those in the mining sector, you see yourself dangling at the very bottom. Only the tobacco industry is less trusted than the mining industry. So we're talking here about trust, not about social license to operate per se, but actually what underlies that. Why is it so difficult to get that? It is because the public doesn't trust the mining sector. And yes, this data is from 2020. Later data shows exactly the same picture. We also found it in our work. So what's trust then? So I'm a psychologist by training, and psychologists thought long and hard about what does trust mean. And I'll save you all the internal debates. But there is some consensus that trust has 3 different elements. We can talk about trust in ability. Can you actually do the job? Do you have the competence? Do you have the skills? Can you organize yourself properly? There's trust in integrity. Are you honest? Are you transparent? Will you actually follow through with your commitments? And there's something called benevolence. And benevolence is referring to, do you act in the interest of society? So actually, are you helping humankind? Are you contributing to society? Will you give us something back for all that technology? So there's a poster in the poster session that looks at these elements, and I can tell you, our data also shows that on these three components, mining sector isn't doing so well. Now, I think most people in mining sectors thought about ability, also thought about integrity. But this benevolence thing is actually interesting because it looks back a little bit of why should we not just look at SLO? Why should we actually look more at this benevolence factor? And this is what we call in the project something called shared value. And shared value is a business model that goes beyond compensation, that goes beyond philanthropy, but is actually looking for competitive advantage in societal challenges. So by helping society, you can also profit. You can also generate competitive advantage. Now, if you want to know more about that, go to our website. There is a fantastic talk of Jocelyn Fraser, who actually explains in detail what shared value means and gives examples of how that can be applied in a business sector. So the other thing we do in this project, and I'm going to just point at different posters and talks here, is we, as Chris also said this morning, we actively think about how to communicate. So Lucy Blesser-Hassett has a poster with a toolkit to stimulate critical thinking in this area. Rosie Carroll is going to talk about how can we actually, in a formal educational setting, discuss these very contentious topics. And there is a video demonstrating a Restore Summer School where we actually train PhD students, early career academics, to critically think about social and geoscience challenges in this field. And this is the Vector project. The vision of Vector is to look at these social components, merge them with geoscience knowledge so that at the end of the day we can communicate to decision makers both social and geo elements that should underlie their decisions. If you want to know more about the project, go to the website. And then I want to hand over to Pat Meere, who is going to talk about two other flagship projects also funded by the EU. Pat?
Thank you. Thank you, Geertje. Morning, everybody. I'm going to talk, I suppose, the kind of the key message I want to get across here is the impact in terms of the iCRAG environment providing leverage and very powerful leverage for securing funding, particularly EU funding. So I'm going to talk about just two projects. One that's just about to start, and one that's just completed. And hopefully it'll give you a flavor and illustrate some of the kind of the key messages in terms of how that funding was leveraged. I'm going to start with our own project here. This is Former Fluid. This is a doctoral network, as you can see. We have 12 partners from right across Europe, a good mix of partners in terms of industry and academic partners. We've got the survey in there as well. But importantly, particularly in light of Chris's and Geertje's talks, we've got a dedicated science communication partner sitting in the mix as well, which is very, very beneficial. We have a total budget of 5 million. We went over, because the limit usually is 4 million for these projects, but the UK, we've got St Andrews as part of the team, and the UK Research RI added $1 million to the kitty. UCC is coordinating, and it's just about to start. We're in recruitment stage at the moment. So apologies for the logo there, but we have 18 PhD projects, and they're, in terms of science, they're divided into 3 distinct work packages. We're looking at fluid flow drivers, so tectonics, gravity, heat sources from high-level intrusives, etc. Fluid flow pathways, and obviously the anisotropies in the Earth's crust that control that, fracture networks, etc. Periodic versus a consistent fluid flow. And then at a kind of a smaller scale, fluid flow interactions, looking at fluid wall-rock interactions, the drivers for precipitation in particular settings, and looking for alteration in terms of fluid flow vectors, etc. Very, very multidisciplinary. So we've got traditional structural, microstructural studies, geodynamics, modeling, petrology, geochemistry, and rock magnetism. So quite a multidisciplinary approach. As I said, we're recruiting right now, so I'd ask you to put the word out. This is our webpage. Please look us up. And if you think there's anybody out there in terms of looking for a research career in this area, please spread the word. Okay, I'm going to move into an area that I'm less comfortable with now, because this is a project that has just finished, but a really, really cool project. This is the Green Peg project, and this is all to do with pegmatites. Julia Menuge is very much, in terms of the UCD lead on this, couldn't be here today, so I'm stepping in to helping out with this. So basically, again, a good spread of partners right throughout Europe, a good mix in terms of intersectorial mix between industry and academia. And the focus is on pegmatites, and obviously they're particularly rich in critical raw materials, particularly lithium for EV batteries, etc. The approach they took was on 3 different scales, from the provenance scale to remote sensing, to district scale, to prospect scale, right down to the outcrop scale. UCD picked up the prospect scale, and this story, I suppose, is a nice, basically, if you like, illustration of how iCRAG engineered almost the funding to some extent. The story starts with iCRAG 1, and this is work done in TCD, looking at using laser ablation mapping, chemical mapping of, in this case, muscovite minerals associated with a pegmatite deposit. They focused on muscovite because it basically tracked the full crystallization history of this particular pegmatite. So that basic research basically allowed Julian and his team in UCD to, I suppose, take that information, that knowledge, and apply it to exploration. And how they did that was that they picked on a mineral, a robust mineral, because things like spodumene, which is the pyroxene rich in lithium, which is the target, particularly in tropical areas, isn't that robust as a mineral and tends to break down. So garnet is a good proxy for sourcing these pegmatites. Again, we've got these amazing chemical maps of the garnets in this case, and those maps, they were able to link them back to the chemical zonation story, crystallization story from the lithium pegmatite, and basically that allowed them then to, if you like, take that information into the field, look at stream sediments and look at these garnets and explore and track back to the original pegmatite sources. This is amazing geochemistry, so I'm going to hand over now to Dave Chu from TCD, who's going to talk to you a little bit more about the geochemistry here. Thank you.
Thanks very much, Pat. So I'm here to talk to you today about the geochemistry platform. So iCRAG has several platforms which are integrated into our research challenges, both supporting them and also performing their own fundamental research. So the geochemistry platform is both integrated into the raw materials and Earth system change challenges, but also performing its own fundamental method developments. So because we're talking mainly about raw materials and resources in this session, I'm going to talk about our work in helping us understand better how we can provide materials that are needed for the green transition. And there's going to be two main themes. They're going to be sustainable, safe production to meet our increasing demand and meeting building targets. I'll talk about the redress scheme that has already been mentioned, and also the sustainable supply of raw materials, both exploration and also recycling of mine waste. So the geochemistry platform is based in TCD, where we've got scanning electron microscopes and mass spectrometers, in UCD, in the National Center for Isotope Geochemistry, where there is extremely excellent mass spectrometry instrumentation. And also, here's an example from UCC, where they have got a Raman set up, and this is some of the work done by Richard Unit and road aggregate technology, where he's developing new methodologies to determine the frictional properties of aggregates. And here's a lovely image, digital metrology and Raman, of a high polar stone value aggregate. So one of the main things that we're investigating in the geochemistry platform, particularly when it comes to construction, is the presence of deleterious minerals in building materials. This is an extremely large problem in Ireland. We've gone from having about 2 decades ago from pyrite-induced heave in floor hardcore to now a new problem, the presence of deleterious minerals such as muscovite, pyrrhotite, and pyrite in aggregate masonry concrete units or concrete blocks, particularly in the northwest of Ireland. It's a key €2 billion issue, €2 billion issue. So the iCRAG labs in TCD are developing automated scanning electron microscopy approaches for quantifying the concentrations, in particular of sulfur-bearing minerals. These are fine-grained materials, and it requires extreme magnification, and that's why we need to use SEM. We're also developing approaches to try and quantify the speciation of sulfur in these minerals, the presence of potential sulfate attack, and also quantifying the amount of very fine-grained free mica in these concrete blocks. iCRAG labs in TCD and also in UCD are pioneering new imaging method approaches, be it by SEM, such as this image up here, by laser ablation, both integrating major element maps with maps down to the ppm level, and also scanning electron microscopy approaches for determining mineral phases rapidly using elemental detectors on some of our SEMs. This is an example of a sandstone, the fine-grained portion of a sandstone, the heavy minerals in the sandstone, and rapidly identifying the phases so we can do provenance analysis on these samples. And one of the things that we're interested in doing is, because these approaches, they're quite time-consuming, is we're actually going to go back a bit now to a more old-school approach, and potentially in future research is going to apply a bit of AI by taking optical microscopy images, which are quite rapidly acquired, and then integrating this with SEM. And this is going to be a potentially new, exciting future development, because optical microscopy is rapidly acquired, and as we can see from the next point I'm going to make, we are going to have to acquire a lot of data and a lot of different rock samples in the future. We're applying these imaging techniques to critical raw materials in ores and waste. We're trying to effectively go all the way through the life cycle of mineral deposits, from exploration, such as the examples presented by Pat Meere. This is a cesium distribution map and a mica from a lithium pegmatite from the GreenPreg project, all the way through to mine tailings. And we've been investigating in iCRAG a variety of different tailing deposits, both by SEM, backscatter images, and elemental EDS images as well. iCRAG's also an former iCRAG researcher, Ling Li Zhu from UCD. She's characterized critical elements in a variety of different Irish tailing deposits from old Irish mines in a project funded by GSI. So, the idea behind this is that we really need in the future to characterize a lot of material. Ireland's got obligations under the EU CRM Act to establish a database of all the closed and abandoned extractive waste facilities in Ireland and adopt measures to promote the recovery of CRM from this waste. iCRAG has also been undertaking fundamental method development in the field of geochronology. We have extreme expertise here. One of our researchers, Emma Tomlinson, is an ERC project investigating how the cratonic lithosphere forms. And she's been looking at garnet inclusions in diamonds and obtaining some extremely young ages, much younger than previous old ages from these rocks. This has implications for the age of diamond, and also it suggests that the cratonic lithosphere, potentially, if these ages are robust, is much younger than in places, much younger than previously anticipated. And finally, some new exciting developments, both in UCD and in Trinity. We're trying to develop a new approach to rubidium-strontium dating by laser ablation, MS mass spectrometry, to date a whole suite of potassium-bearing minerals in ore deposits and other geological settings. So I hope that gives you a flavor of some of the work that the geochemistry platform has been doing, and I think I'll pass back to Koen for the final wrap-up.
Thank you, Dave. So Dave has explained how the geochemistry platform works, and I want to take you to a slightly different scale. So from the inception of iCRAG, we have been working on the Irish subsurface geology, especially the Irish Carboniferous basins and the Irish ore field. So many of you will know, and some may not, that Ireland hosts important mineral deposits for zinc and lead. And there are active mines, and there were active mines, and there's active exploration going on in Ireland. So this is just a snapshot of the multidisciplinary approach, which, and I'll get to that, leads into some surprising spin-offs during the program of iCRAG. So this slide shows you a seismic line on the bottom. So this is deep earth imaging the layers of the Carboniferous basins and its older basement for several kilometers depth. And it's showing you in pink the basement geology underlying the Carboniferous basins, and a large 3 to 4 kilometer throw fault, the Navan fault, which hosts in its footwall the Navan deposit, one of Europe's largest zinc mines. This was work done by several researchers, 5-6 researchers, as part of research in the early stages of iCRAG, and that has resulted into a regional scale geological model of the subsurface of the Carboniferous in Ireland, and as well as several mine scale models which have been published in a number of papers over the years. And working across scale and using those big scale insights, Lola Yazaris, who was a postdoctoral researcher in iCRAG, looked at the pyrite minerals in the cover above the mineral deposits to see whether we can actually explore for them without actually drilling into these really deep basins. And so she found that there are sedimentary exhalative halos of pyrite that can be fingerprinted near the faults. Another application in the same mine setting, and I'm just using the Navan Tara mine as an example, is the Tara Size project, which was run at Dias, which monitors the rockburst events that are happening in Navan mine. And an obvious synergy there is obviously that all of these data are co-located. So you have a spatial component, which is what we as geologists like to do, and where we can offer the expertise. A lot of these projects are co-funded with industry partners, as so much of our research is. So I mentioned to you when I first appeared on stage that we have to be global in our approach. So when we talk about reliable, sustainable supply of critical materials, you could go back in the value chain of raw materials and look at the global distribution of where our batteries and EVs are being produced. This is from 2023 by the International Energy Agency. You can see there is a dominance of certain geographic locations, and if you put it back into the raw materials value chain, you look at materials processing, putting the elements together to build battery cells and EVs. Okay, there's also a certain geographical spread across the world. And if you look at the actual mining activities and the mineral exploration, there for certain key elements like lithium, nickel, and cobalt, there are key players in the world that have certain dominance at the moment. So to address the EU Critical Raw Materials Act and that fourth bullet I was explaining, we do need to work globally, and that is what iCRAG is doing. Since the beginning, we have been doing projects with various partners across the world, mainly on the left side of the map, as you can see, to improve the knowledge of the geology and the genesis of mineral systems in key districts, tying in with the previous graph I was showing, developing and applying these new exploration and processing technologies that Dave and Pat were explaining, and also nurturing partnerships, applying some of the insights that Geertje was talking about globally. Just one example of how we're doing this, there was a UNESCO lecture series on Earth Materials for Sustainable and Thriving Society, which included iCRAG lectures, which was co-organized by the International Union of Geosciences and iCRAG, and had many, many registrants from many countries across the world, addressing this challenge, combining the social aspects with the detailed research. And just to highlight that there are several posters of projects like this that will be on display during the break, ranging from projects in Peru, looking at regional scale mineral systems analysis using seismic data, which was originally shot for hydrocarbons exploration, looking at the copper, gold, silver deposit Nautanen North in Sweden, so EU mineral deposit research, and also going to Namibia, South Namibia, looking at the Roshpina zinc, lead and silver deposit, where we're applying insights and comparing them to other districts worldwide to get more insights into how zinc and lead systems developed, with various collaborating and co-funding partners in the private industry. So with that, I'll pass on to Emer so we can go into the break.